Let's begin with the discussion of Part A of the experiment, which involves the compound sodium percarbonate. Sodium percarbonate is, ironically, what's called a non-stoichiometric compound, which consists of a complex of two or more smaller molecules with a non-integer number of one molecule with respect to the other. So here, for example, we should expect that in general, n will not be an integer. In fact, the value of n depends on how the sodium percarbonate was prepared and its age and some other factors. And so we're not really going to have a firm known value here for the number of H2O2 molecules per sodium carbonate molecule. However, what we can say just to ballpark it is that this should be somewhere in the range of 1 to 2 H2O2 molecules per sodium carbonate molecule with a little bit of wiggle room above and below. So our goal in this part of the experiment is to determine this value of n. And the first thing we should say about this value n is that you should consider it as a molar ratio. It's equal to the moles of H2O2 in some sample of the compound, any sample of the compound really, divided by the moles of sodium carbonate in that same sample. One thing to note here is that although that n appears in the molecular formula, the ratio of H2O2 molecules to Na2CO3 molecules within a single molecule of sodium percarbonate is the same as the ratio on the molar scale, since all we're doing in going from molecules to moles is multiplying by Avogadro's number. So our goal here really, and since experimentally we'll be working with numbers of moles on a relatively large scale, our goal here is to determine the moles of H2O2 in a sample of this compound per mole of sodium carbonate. And to do this, we're going to take advantage of a specific reaction of the hydrogen peroxide component of this sample. Specifically, when we take sodium percarbonate and we dissolve it in water, it separates into the sodium carbonate and hydrogen peroxide portions. And the aqueous hydrogen peroxide that forms, when placed together with aqueous iodide, or I-, and a strong acid such as H2SO4, which we'll represent just as H+ here, these reagents combine in a redox reaction to form water and an oxidized version of iodine that's called triiodide, or I3-. The whole idea behind the method of iodometry is to measure the number of moles of an oxidizing agent such as H2O2 in a solution by studying its reaction with I-. We can reason here that if we know the number of moles of triiodide that formed as a result of reaction with the hydrogen peroxide, well then of course we can reason our way back to the number of moles of hydrogen peroxide using a simple molar ratio. But to measure the number of moles of triiodide, we actually have to take advantage of another reaction that consumes the triiodide. So I3-, which I'm going to draw here in blue, and the reason I'm drawing it in blue is going to become apparent in a second, is going to react with a known amount, a known number of moles of the reagent sodium thiosulfate, which contains thiosulfate anions, S2O3 2-, in aqueous solution. And this simply undoes that oxidation of the iodide to I3- and forms 3 I-, or iodide anions, and an oxidized version of thiosulfate, S4O6 2-. We will know, based on measurements and how the experiment is set up, the number of moles of sodium thiosulfate it takes to fully consume all of the I3- in the solution that's set up as a result of reaction 1. Hence, we can work our way back using a molar ratio built into the chemical equation for reaction 2 to the moles of I3- in that solution, and from there, as we mentioned before, back to the moles of hydrogen peroxide. That amount of hydrogen peroxide then simply is the moles of H2O2 that appears in this molar ratio. I'm not going to say too much about how to calculate the moles of sodium carbonate because this is all theoretical. We actually have all the information we need once we have the total sample mass and the moles of H2O2 to calculate the moles of sodium carbonate in the sample. I'll only mention a couple of points here. The first point is to think about the mass of H2O2 in the sample and how to calculate that. And the second is to think about how the law of conservation of mass can help us here. Specifically, the idea that within this compound we have only sodium carbonate and hydrogen peroxide. In part B of this experiment, we'll be dealing with a mixture of sodium nitrate and sodium chloride, and the goal will be to determine, in essence, the amount or mass of sodium chloride in the mixture, and more specifically, the mass percentage of sodium chloride in the mixture. So this just gives us a metric of the percent by mass, or in a 100-gram sample, how many grams of sodium chloride do we have in the mixture of sodium nitrate and sodium chloride. And in order to do this, we're going to take advantage of a titration that allows us to determine the concentration of chloride and then use stoichiometry to determine the moles and mass of sodium chloride in the mixture. So we'll start with essentially a pile of solid mixture that contains both sodium nitrate and sodium chloride, and we're going to take a portion of that, a known mass, let's call that m tote for the total mass of the mixture that we take and dissolve in water to create an aqueous solution. And in this aqueous solution, we're going to have three different types of ions dissolved, three different types of solute ions. We're going to have the sodium plus cations, and those come from both the sodium chloride and the sodium nitrate. We're going to have the nitrate ions, NO3-, and we're going to have the chloride ions, Cl-. And really where we're going from here experimentally is to determine the number of moles of chloride ions through a titration. To do this, we're going to take advantage of the fact that silver plus cations, Ag+, combine with chloride anions in aqueous solution to form an insoluble precipitate of silver chloride, or AgCl. This precipitate is very fine and fairly cloudy, so it's difficult to determine exactly when we've added just enough silver to consume all of the chloride in the mixture. So we have to take an extra step in order to identify the endpoint of this titration, the moment where we've added just enough silver plus to consume all of the Cl-. And that extra step is going to involve dissolving potassium chromate in this solution as well. And so we're going to have K2CrO4, which is going to leave dissolved 2 K plus ions and 1 CrO4 2- ion per formula unit of K2CrO4 dissolved, of course, in this solution as well. The reason we need to do this is so that we can tell exactly when excess silver has been added. At the moment we've added just enough silver to consume all the chloride, the next drop of silver solution that we add is going to form a new insoluble precipitate with a different color. Specifically, the silver plus cations, specifically two of them, are going to combine with the chromate anion, CrO4 2-, to create an insoluble orange-red precipitate of silver chromate, Ag2CrO4 solid. This orange-red precipitate is going to be indicative of the endpoint of the titration, since it's only going to appear just after we've consumed all the chloride in the solution, and the silver plus has no choice but to pair up with the chromate anion to form Ag2CrO4. To actually accomplish this titration, we're going to add silver in the form of silver nitrate via a pipette. And this is a little bit different from part A, because this silver nitrate solution that we're going to add, we're going to do so using a pipette rather than a burette. And the reason is we don't need to add that much, and the concentration of the silver nitrate solution that we're going to use to add silver plus cation, that concentration is listed in units of weight percent, specifically 1.7% by weight. And so what we can do is mass the beaker with the solution in it initially, add titrant until we reach the endpoint, until we see this orange-red precipitate, and then mass the beaker again with the titrant in it to determine the mass of titrant added. That mass of titrant added can be related to a mass of silver nitrate delivered via this mass percentage concentration. And ultimately, this is going to allow us to determine the number of moles of Ag+ that we added in to consume all of the chloride in the solution. Thanks to this 1-to-1 mole ratio between Ag+ and Cl-, we can then conclude that the number of moles of chloride in the original solution, the solution of the solid mixture that we dissolved in water, that number of moles of chloride in the original solution is equal to the number of moles of silver plus cation added via the titrant.
And I won't fill in the details here, but it's pretty straightforward stoichiometry to go from that number of moles of chloride to the number of moles of sodium chloride that were present, say, in the original solid that we dissolved, and then from there to the mass of sodium chloride in that original sample of mixture that we dissolved. And of course, once we get to that point, the mass percentage of sodium chloride in the mixture is just that mass of sodium chloride that we measured divided by the total mass, which we measured by essentially weighing out the solid on a balance at the start of this part of the experiment. Multiplying that ratio by 100% is going to give us this mass percentage of sodium chloride in the mixture.